All right, hey, Three Rivers students, Mr. Martineau here. We're going to do lab number 5. So this is our continuing series of taped demo labs that you guys have to watch. So the lab write-up right now says it's for a half Atwood machine, which is what we have in front of us here, and then a full Atwood machine. To be honest, I failed to procure the equipment for the full Atwood machine. So that is probably going to end up being another video, probably someone else I find on YouTube, and I'll give you the data for that. So for right now, and I'll explain that a little bit better when I see you on Thursday, but right now we're going to do the half Atwood machine live, and the full Atwood machine I'll have to give you an even more simulated simulation. So let's just worry about the half Atwood machine right now. So as we have, as we saw in our free body diagrams, we have a half Atwood machine. This is considered to be frictionless, though it's not, so there will be some experimental error in it. Half Atwood machine consists of a falling mass over here and a sliding mass over here. Again, we're assuming a frictionless environment. I know for a fact that's not, but we are going to assume a frictionless environment. The goal of this lab is, as you saw from the derivation, if we alter M1 and M2, or the falling mass and the rolling mass, we should get different net accelerations for the system based on M1 and M2. So that's basically what we're trying to test. In your derivation, you derived an expression for the acceleration of this system without actually getting the time. So the acceleration of this system you derived in terms of M1, M2, and G. That's all nice and all, but that's a perfect system. Well, we don't have a perfect system. The system we have here is, well, a real life system. So there must be another way to measure the acceleration. Well, one way we can do that is, oh no, I need a stopwatch.
Here.
I realize that. How do I do this?
Hit the home button. Excuse us. Yeah. Usually, yeah, there you go.
Sorry, guys.
And just go to stopwatch.
Okay.
And there you go.
Cool. Sorry. Didn't even think of that. All right. So we have a theoretical acceleration in terms of M1 and M2, but now we need a measured acceleration in terms of the kinematics of the situation, which is going to be the time it takes the car to roll or the mass to fall, and the distance through which it displaces. So what we know, one thing for certain, is that the distance that weight falls is going to be the distance that car rolls, because they're related to each other, right? And we're only taking data from while the weight is falling. So we only really want to worry about the distance that weight is falling. I measured that already, and it's 0.6980 meters. So to 4 significant figures. This will change a little bit, but we're just going to keep that as a number. So eventually you'll see that I'm going to hang another weight from that weight, and you'll say, well, it's not falling the same distance anymore. I'm not going to remeasure it. We're just going to put it in as systematic error, just because we're just going for proof of concept. Okay. The point of this lab is that we're going to change the mass of the hanging mass, and then time how long it takes to fall. We're going to change the mass of the rolling mass, and we're gonna figure out how long that takes to fall, and then we're going to record all of our data. So let me reference this data table again if you come over. So right now we want to get a good shot of it. You're going to write this down in your own notes. So we have, this is the distance, it's the same every time. This is the mass 1, the falling mass. This is mass 2, the rolling mass. Now to be honest, I don't remember in our derivation which one we called which. If we called M1 the falling, or if we called M2 the falling, and it doesn't matter as long as you know which one is which here. These are the masses I'm going to use. They're pre-prescribed, so I'm not going to even think about it. And then as we run the lab, I'm going to write down the time it takes the falling mass to fall. That's the only thing we're worried about, the time it takes the falling mass to fall. Okay, so last thing I want to say here is I don't have a triple beam balance, but that's okay because they make this equipment so that we don't need one. These masses are marked at 20 grams. The manufacturers of this cart report that the mass of this cart is exactly 0.5 kilograms. It's not, but within plus or minus 1%. And these metal blocks, you can add to the top of this cart, and they make it so that these metal blocks are exactly the mass of that cart. So if I have 2 of them together, it's exactly within tolerance, 1 kilogram. So this is 0.5 plus 0.5. So that's how I'm doing all this. So in case he's not measuring anything. They are all pre-printed, so there's no guesswork. Okay, so now what we're gonna do is we're gonna run the lab. So the first thing we're gonna do here is I'm gonna have the falling mass is 0.02 kilograms, and we're gonna have the rolling mass at 0.5 kilograms. All of this will be in the data table later. So, oh, these iPhones, I don't get them. Okay.
It's a good phone.
I know it's a good phone. All right, so I gotta eyeball this over here. So we're gonna go 3, 2, 1, go. So it's 2.80 seconds. So I'm gonna write that down. Okay, so there's our first trial, okay? Second trial, reset. All right, so the second trial is gonna be 0.2 over here still, and now the mass is gonna be 1 kilograms, right? So what we'd expect, we should get a different time, and hopefully we do, or physics is broken. Here we go, 3, 2, 1, go. 4.25 seconds. So we get a longer time, which is what we expect. Is that the cat?
That's the cat.
That's not our cat, by the way. Okay, we're gonna reset that. Next one is 0.04. So the way we're gonna do 0.04 is we are going to attach a hanging weight to the bottom of that weight. All right, so yes, the distance is now different. I'm not gonna worry about that part too much. Okay, because again, there's gonna be some error on everything, but really we're going on proof of concept here. So we're gonna go 3, 2, 1, go. 1.77 was the weight, was the time. This is not easy.
No.
1.77 seconds is the time. The next one is gonna be 1 kilogram here, and then 0.04.
Am I allowed to show the cat?
Oh, sure.
Hi, kitty. Hi, kitty boy.
That is not our cat.
Nope.
We don't know his name. We don't know where he lives.
Nope.
He just comes by to say hi.
And bring us
And
dead
bring us
things.
dead things. A lot. Big dead things. I'm surprised this pulley is even staying. See, we got some error here because this pulley's broken. So there's some friction right there. So there's a lot of error, but we should get within. We should get within. All right, here we go. Clear that, reset. 3, 2, 1, go. 2.25 seconds, which makes sense with the other data. And lastly, oh boy, we're going big time. We're going 60 grams on the end. So this is going to be a fast one, I think. Probably have a lot of error on it. Just, oh, I was hoping that wasn't going to happen. Not that. Hang in there, folks. I am not the knot king. I did not do the Boy Scouts. Okay, so here we go.
You to make a square knot.
Yeah, that's right. We're just going to go with it. Oh. Experiment's over. Okay. That's it. I'm done. Okay, so let's take a look at the data that we have. We can go with 4 points. It's not the end of the world. So that's my data. We're going to scratch this one. I'm not setting it all back up. So there's my data. Can I?
Yeah.
All right. So we got 0.28, 2.8, 4.25, 1.77, and 2.25 seconds. And that was the same displacement each time at 0.6980 meters. These are the masses. Look at me again.
Mm-hmm.
Super. So again, that's the half-hour machine. There's some error. Again, we had some error in the pulley and the rope. I know for certain that these wheels are supposed to spin freely. And they don't, so these are just rusted out and old. But still, we should get reasonably okay results. And again, this is one of those things where you guys want things to be on the nuggets, but the theoretical acceleration, the one that we derived in class, and the measured acceleration, the one we just took with the stopwatch and the meter stick, should be close to the same. So probably my guess is going to be it's going to be like 20% error. That's going to be my guess. But it's okay if there is. Again, that's for the half Atwood machine. The full Atwood machine, I don't have the apparatus for it. I failed to get it. That's my fault. But I will either post a video online or I'll just give you a data table and describe what happened rather than seeing it in realsies. So that's the deal. So coming to you from the House of M, Mr. Marno here, my wife, Ms. Mangiarelli on the camera, Twins is the cat, who is probably gone. And thanks everybody. And if you have any questions, please email me, get me through Teams, and good luck with the analysis. Thank you very much.